All right, welcome everybody. This is really great to see a good number of people from the delegate crowd to participate in today's assembly. Today, we're very lucky to have the very first presentation by a person who's not directly a member of the community engagement team. Yusra AlSayyad is working primarily on Lsst science pipelines and I believe also algorithms and so on and so forth. So this is really great to see her on our venue here. As Melissa might have mentioned, we are very interested in having you suggest a breakout topic, and you can actually send it, as she said, via Zoom to us, and we'll add it if it's something that you are interested in doing. So the plan for today will be that there will be a few more announcements that Melissa will make regarding the this new thing called Dp0 Delegate Profiles, and then shortly after that, we're going to start with the main presentation. So maybe you should take it away, Melissa, at this point.
Yeah, I'm going to do a few announcements. Thanks, Greg. The first announcement is more of a reminder of all the delegate resources and activities that are available for you, and just a quick look ahead at our delegate assemblies and the topics coming up over the next couple of months. In 2 weeks, we'll be doing data visualization. 2 weeks after that, some image processing. And then we have some pretty much like empty sessions for delegates to present their own work that they've been doing with Data Preview 0. And so far we have one volunteer to make a presentation in November, but we're looking for more volunteers. So if you've been working on something that's related to Db0 science, you need a notebook, you did an investigation, anything, it can be quite short, even if it's just like anything from 5 to 10 minutes up to a full notebook of 30 minutes. Literally anything you'd like to present, just get in touch. You can send me an email or a direct message in community, and I'll help get you into our delegate assemblies schedule. And that'll be like for the first hour when we're doing more formal presentations. And of course, at any time you can volunteer to present or run a breakout session. Along with that, sort of trying to enable Dp0 delegates to present and share their work, I just wanted to give a quick reminder about Dp0 Working Groups. We're hoping that those would be very grassroots in the way that they are formed. It's whatever delegates want to do and want to get together and work on. We do have a repository on GitHub where you can share your notebooks. And to kind of try and take a first step, I've made a new supernova shared folder and put one new notebook in there that has to do with making a supernova light curve. And today I'm going to try and run a breakout session about supernova and try to kickstart a little supernova working group as a first example. And as always, everyone's welcome to come to the Stack Club, very informal co-working sessions that run at this time, but on the alternating Fridays with our delegate assemblies. So all of that is still there and still open to you. Another reminder that's not on here is that we have a Db0 survey that's open right now, and you're going to get an email reminder about it from me probably on Monday, because the deadline for that survey is next week. And so thanks to everyone that's already filled out that survey. We very much appreciate it. The next super brief announcement is just a really quick reminder about the Preparing for Lsst Kickstarter proposals that are also due at the end of the month. This is for people who are in the TVS, Stars, Milky Way, Local Volume, or Solar System Science collaborations. And so I just wanted to pop up that link right there to remind you that proposals to support your Dp0 related work on these topics would be very appropriate for this call for grants. So you know, get on that if you're interested in getting money for your work. Another just super quick announcement from the science collaborations about their New Friends program. It's up, it's running. We're still looking for people who are long-term members of science collaborations to be new friends with our new to Rubin people who have come to us through Data Preview 0. So that form is still open. If you're interested at all in that program, just please get in touch. Next announcement for today is we're trying out this new thing that we're calling Delegate Profiles. It's going to be a new feature of our delegate assemblies. And for today, we sort of invited a random subset of delegates to give like a really quick single slide 30-second introduction to themselves and their science interest regarding Rubin Data Preview 0. The reason we're doing this is to try and better enable networking between delegates and to inspire more collaborative work together, to inspire more working groups. It's really hard to do that since you're all sort of from all over the world, and most of you don't know each other already. And so we're trying to provide this opportunity to let people introduce themselves so you can get to know each other a little bit better. So we're going to do one delegate profile at the start. Usually we'll do, we'll try to do like about 20 profiles right at the midpoint of every delegate assembly to provide a nice break between the formal presentation and the breakout sessions. But we know that that timing doesn't work for everybody. So we'll also do a couple of, at least one little delegate profile right at the start here today. So how this is going to work is that in the future, we'll be sort of inviting like a random another 20 delegates sort of every 2 weeks to make a delegate profile until we've worked our way through everyone and everyone has had an opportunity to present. So watch your inbox for that invitation coming later. So we're going to kick this off right now with at least one delegate profile. If you are here and you've put a slide in the deck to present at the midpoint, but the midpoint timing doesn't work for you and you'd like to present now instead, just put your name in the chat. Let me know via chat and I'll display your slide here in our first little block. So really let's start some delegate profiles. I think we have Akhtar here. If you like
yes, hi, Melissa. Can you hear me?
Yes.
Yes.
Great. Do I have to have the video on? I'm not sure if that's working.
I can see your video and we can see your slide. Yeah.
Okay. Okay, thank you very much. My name is Akhtar Mahmoud. I'm from Bellarmine University. Bellarmine University is part of the Kentucky Association of Research with CARL, or with LSST called CARL. And there are 8 universities in Kentucky that are part of CARL. And we are a LSSTC member institution. And I'm serving as the rep for this academic year. In terms of my career level, I'm a professor of physics. And my background is experimental high energy physics. So I'm transitioning to cosmology and astrophysics. So I'm learning a lot. I've been working with desks for since 2018 on the FOSIM project and the HPC cluster that we have here. We generated the LSST Survey 1 FOSIM data sets. And that is available in the public domain. If anybody's interested, let me know. So my interest is essentially in the exploration of dark energy with DESK to pursue precise and accurate cosmological studies using weak lensing at the pixel level. So I'm very interested in working with others in weak lensing. If you know anybody, please let me know. I'm going to be hiring a postdoc to work with me. So that's all I have to say for now. Thank you.
Great. Thanks very much, Akhtar. It's nice to meet you. Thanks for being here and participating in the delegate profiles today. If we have anyone else who's giving a profile at the halfway point who would prefer to speak now, because maybe you have to drop off at 10, maybe just unmute or let me know in the chat. I'm going to count to 10. Oh, okay. Yeah, Alex, let's queue you up. We'll do Alex and Yanni now. Okay, perfect. Alex, yes.
Sorry, give me 1 second.
Okay.
Let's see. Okay, can everyone hear me okay?
Yes, I can hear you.
Okay, I'm Alex Galliano. I'm a 4th-year graduate student at the University of Illinois at Urbana-Champaign. I study various problems in time domain. I'm really interested in the host environments of different explosive transients. And I'm involved with Db0 because I'm one of the people leading the charge for simulated LSST alerts for the Elastic Challenge to validate broker systems. So I'm really interested in learning about right now what is planned for the different data products and how they're going to be presented through LSST infrastructure. And it's nice to meet everyone.
Great. Thanks, Alex. Thanks for being here and for giving a little delegate profile. We'll put in one more at the start. Yanni. Hey.
Okay, let me just introduce myself. Hi, Melissa. Thanks. Hi, everyone. Right, so I'm a senior astronomer at the University of Heidelberg in Germany. Before that, I used to work at Las Cumbres Observatory, and this is where I know Melissa from as well. So in In terms of my interests, my background is in exoplanets, specifically gravitational microlensing. I've been working in the field for about 20 years or so, but I also do transients and variable stars. And I'm quite interested in harvesting alerts from different surveys and scheduling follow-up observations. I'm also working on the TVS portal, and we're doing an in-kind, I'm the head of the in-kind contribution for Heidelberg University. We're a small group, 3-4 people, but we could grow. So the people that are directly involved in the in-kind contribution are myself and Marcus Hundertmark. I'm also very active in public outreach. And what I want to do in Dp0, I want to learn more about the Rubin Science Platform and become familiar with the Butler system. I quite like the Jupyter notebooks up to now. I have found them extremely useful. And I want to understand more about the, what various options are available to extract, display, interact with the data programmatically. And yes, I would be very interested to collaborate with any of the other Dp0 investigations on similar topics. Thanks.
Wonderful. Thank you. Thanks, Andy. Thanks for being here today. Okay, this was great. So hopefully this brings a little bit of a personal aspect to our delegate assemblies and gets people to know each other. Let's do the rest of the profiles at the break as planned and turn it back to Greg and Yusra. I'm going to stop sharing my screen.
All right, Yusra, I'm assuming that you have few slides that you would like to show. So at this point, maybe you should just take it away and we'll listen.
Okay, thank you.
Right,
the host has disabled participant screen sharing.
Oh, sorry. I guess that's me. Let me,
While Melissa enables that. Hi, I'm Yusra AlSayyad. I'm a postdoc sitting at home in Princeton. I'm a member of the Algorithms and Pipelines team, which in the construction era was called the Science Pipelines team. Let's see if I can. Yep, thank you, Melissa. The Algorithms and Pipelines team is the group that is writing the software that's going to process the raw images coming off the telescope and convert this multi-epoch, multi-petabyte data stream into catalogs and data products and images for you to use for your science. Last session, Alex showed you how to retrieve these images and catalogs using the Butler, and you saw him retrieve things with funny names like CalExps and deep coed force sources. And today I'd like to go over how those different data products were created and what they are. So we'll spend maybe 25 minutes going through some slides that will give a good overview of the pipelines. And then we'll go through notebook number 5 as a continuation of this curriculum. In notebook number 5, we're also going to learn how to reprocess some of these steps yourself. The building blocks of the science pipelines are called tasks. And in this notebook, we'll also get an introduction to tasks, and you'll see how to run some tasks yourself. Any questions before we kind of dive into pipelines? Okay, some background info on pipelines is that the science pipelines are going to get these images and catalogs to you in 2 different ways, both fast and slow. The fast method will be via the nightly alert stream. This is going to support science that requires rapid follow-up. Slow will be in the form of annual data releases. This supports static sky science and statistical studies of variability. A misconception I hear all the time is that image differencing is only going to be run nightly. This is not true. Image differencing is also going to be part of the annual data releases. Remember that one of the main data products that will be released annually are well-calibrated light curves, and we need difference imaging to do that. The data set that you're working with now, Db0.1, is a simulated data release. So the pipelines that I'm going to show now are going to focus on what's run during typical data releases. These are made up of the same building blocks, but what we choose to run in Db0.1 versus Db0.2 versus future data releases will change a little bit. I'm actually, like, we're in the midst of finalizing the pipeline for Db0.2, so that is all loaded up into my working memory. And if anybody has questions about what will be provided in Db0.2, I'm happy to answer questions about that as well. So this is a high-level overview of a data release production. We start with raw images coming in, and we'll produce both catalogs shown in red and images shown in brown. The basic steps, and we're going to go through each of these 4 steps in more detail, are single visit processing, coedition, and image differencing processing, that is detection and measurement on these coeds and image differences, and then using the full stack of images to do object characterization to measure things like colors and fluxes and shapes and light curves. Some project jargon that I'm also going to try to introduce as many terms as possible. You may have already heard some of these. I guess stop me if you already know this, but I'll go through as much jargon as I can as part of this introduction. So some special reserved terms in Rubin are sources and objects. They mean very specific things to us. Objects are, you can think of an object as something real in the universe, and a source is just a single observation of it. So a source is the photons in the image, it's one observation, whereas an object, I think of it as a logical aggregate of the sources. So an objects have the information from the whole survey, and this includes variability information, color, motion, the full characterization. It is not, however, so even though objects are the logical aggregate of sources, a source is an observation of an object, the objects are not literally the matched sources. So the sources are the detections and measurements on the single visits. However, we do not merely just match the sources in order to get the objects. The reason for this is that the single frame images are shallower than the coads. And so you're not getting all the observations. And if you're not getting all the observations, any aggregates based on the highest signal to noise observations are going to be biased. Also, matching blended fields is inherently an ambiguous exercise, and we want to remove that ambiguity. So light curves are going to be produced. They're going to be made available via the force source catalog. Now, the force source catalog is not available as part of Dp0.1. However, it will be available as part of Dp0.2. And my understanding is that there's some workaround notebooks available later in the delegate assemblies on what to do with the sources. This is a valiant exercise. Just know that in the future, when 4 sources are available, this won't necessarily be the recommended way to produce light curves. The other piece of jargon you see, what the hell does DIA mean? DIA is just an acronym that stands for difference image analysis and anything related to difference images. So if sources are the catalog of detections and measurements on single frame images, then DIA sources are the detections and measurements performed on image differences. Okay. Any questions on high level before we go into single visit processing? Okay, so more jargon before understanding single visit processing. 2 weeks ago at the last delegate assembly, we introduced the concept of visits and exposures. Note that we use exposure in two different ways. So yes, exposure in the Butler database is one observation, of which a visit could be an aggregate of one or two or maybe more. In the science pipelines itself, an exposure is it's a class, it's a software object. It's a template, it's templated. So I think in the notebook last time you saw this appear as exposure F. That means it's a single, each pixel is a single floating point. If you see something like exposure D, that means that each pixel is a double floating point. But when I refer to these software objects as exposures, and they're just an object that contains a masked image, which has an image, mask, variance plane, and then a whole bunch of metadata like exposure time, and also some other things like PSF models, WCS models, and photometric calibrations. We refer to these groups of 9 detectors as a raft, and each single CCD or sensor we refer to as a detector, which consists of 4K by 4K pixels. Looking at single visit processing, I annotated this with the data product list that you saw from last delegate assembly. So when querying the Butler, you got a list of all the data set types available. You saw things like raw, bias dark, calyx background source. This is where they come from. So the raw images available are called raw. The calibration data are called bias dark flat. These all go into a task called instrument signature removal task. This is equivalent to detrending. This is flat fielding, bias subtraction, stuff like this, image reduction. This produces an image called a post-ISR CCD, which is an intermediate data product, which is not available in Db0.1. So there are a lot of intermediate data products that are produced during the data release production. However, there's not enough storage space to keep all of them, and they are trivially reproducible by reprocessing them in these tasks, which we'll show you how to do later, which is why we don't store all of them. Okay, then we run characterize image task and calibrate task. These perform background estimation, source detection, source measurement. It also measures the PSF models, the WCS, and the 0 points. These are split into 2 steps because these steps are inherently iterative in nature. You have a chicken and the egg problem with background estimation and source detection because you need a background model to select sources above the threshold, but then you also need to know where the sources are in order to estimate your background. And so there are always going to be a few iterations here. These produce a data product called Calyx, which we looked at last time, and are a primary data product. Attached to this Calyx is the PSF, WCS, and 0 point. What is not attached to this Calyx is the background model. And in the notebook, I'll show you how to read the background model in and add it back. The catalog that this outputs is called source. This is just the detections and measurements. From here, we have a number of global calibration steps. There's a full focal plane background estimation step, which was performed in Dp0.1. In Dp0, so the backgrounds and simulated data are actually very simple. So after some investigation, we've concluded that using this global full focal plane background subtraction task is a little bit overkill for simulated data. So this will not be available in Dp0.2. However, it is here and it's called SkyCore. Because we have perfect reference catalogs in simulated data sets, the global astrometric calibration and global photometric calibration steps were also overkill for simulated data. And so these these were not performed in this data set. Okay, the next step is image coedition. Image coedition takes all the outputs that we have got from the previous step and then takes the calyx and then reprojects them onto a common pixel grid, a common projection, which you have seen referred to as tracks and patches. This is, okay, and this is also not HSC sky map, this is DC2 sky map that I'm showing here. A tract, so this is a sky map is a configurable sky projection and pixel grid that you can then warp your single visit images onto and use for stacking. It roughly, you split the sky up into tracks. Each tract has one WCS, has one pixel grid. This tract is then split up further into patches, just the size of an image that you can reasonably work with and load into memory at a time. This is configurable. It's 4K by 4K now. Another thing to know is that the bounding boxes, like the patches truly are subsets of a larger image, meaning the bounding boxes reflect where they fall in this tract geometry. So if you grab patch 8, for example, and then look at its XY0, it's going to be 4,000, 4,000, not 0, 0. That allows you to trivially mosaic all the patches into a single tract if you so want to. In general, you can think of a tract as something focal plane size and a patch as something detector sized. As you can see in for the DC2 sky map, however, a full then a tract. Okay, any questions about tracks or what we've talked about so far? Okay, now that we've reprojected all the single epoch images into this common tract patch geometry, you can then stack them. So we stack them using a task called compare warp assemble coad task, which finds artifacts, masks them before stacking them. Note that anything that's dashed, any dashed lines I show here are things that are possible via configuration, but we don't run now and wasn't run during the Dp0.1 processing. So this Coedition produces direct coads. This is the deep coad data set that you saw from the Butler last time. Also available is a deep coad N image. This is for QA. So this, if you read it in, it shows you the integer number of images that went into each pixel. So this is sometimes useful for seeing, like, get a rough estimate of how deep your image is. We call these direct. Okay, so there's two ways to describe your coad. One is how many images went into it, and then the second axis is what happened to those images before you stacked them. So deep refers to the fact that every image that was available was included in this coad. Deep is opposed to visit selections such as good seeing coads, which would have only selected the subset with good seeing. That's what the deep refers to. The direct refers to what has happened, how many convolutions has happened to these warps before stacking them. So all direct means is that it's only been warped and no further convolutions have been applied to these warps. Okay, so in Dp0.2, we'll continue on to image differencing. In Dp0.1, this step was not done. Now that we have coads in hand, we're going to run detection and measurement on these. Okay, crossing out the parts that were not performed in Dp0.1, but will be in Dp0.2. The coad process, by processing, we just mean we've run detection on all the bands and taken the union of the detections, and then we use those detections to perform measurement. This is actually better understood if you're trying to map these to the data products that you see in the Butler. There's a chart from one of Jim's papers, which kind of goes into detail of where the different object level data products have come from and how this is performed. Now, this chart was made for HyperSub PrimeCam, which did not have a U band, but imagine there's a U band in this flowchart as well. So the first step is detection on all the UGRIZY coads separately. And then we merge those footprints and those peaks so that we now have one set of the union of the footprints and peaks that we're going to use for all measurement on all bands. Using those peaks, we then run deblending and measurement. And we measure centroids, shape parameters, fluxes. So this is, at this point, the deep coed MEJ data set. And it has, for every band, every object has a different centroid and a different shape parameter. We then take those measurements and select, so you have measurements for all 6 bands. The next step is going to select the band that has had the highest signal to noise measurement, and then use that reference centroid and shape parameter for forced photometry on the coeds again. Now, forced photometry, we use this in 2 different ways too. There's multi-band forced photometry, which is what I'm talking about here, wherein you force measurement at particular centroids and shape parameters on coeds. There's also multi-epoch forced photometry. That's the light curve producing kind that that is going in the force source table, for example. So I will try to modify the phrase forced photometry with either multi-band or multi-epoch when talking about pipelines. So the way the reference bands are selected is, so if it looks at the measurements from all 6 bands, if the I band measurement is sufficient signal to noise, it'll use that. If not, it'll look at the R band. If the R band is sufficient signal to noise, it'll use that. If not, it'll use Z band, and it'll keep going. This builds up a catalog that has the same number of rows as MEJ, but it'll tell you which band was the new reference band. And then using these reference centroids, it'll force photometry, do multi-band force photometry on each of the coeds and produce this deep coed force source table. And this is the primary object level catalog that was recommended that you use a couple weeks ago. And this is where it came from. So each of these catalogs have the same number of rows. They're just measured slightly differently. Okay, so that's actually it for what has happened to the RAWs that have produced the data sets that you see in the Butler. I'm happy to take questions on this stuff before we switch to the notebook and start going over tasks and stuff.
I did just have one question. The U band wasn't in your last slide. Is it, but it's presumably included, and is it just treated so like G maybe?
U band, okay, so yeah, U band, I'm pretty sure comes last in the priority order. So you can, yeah, there would be an extra step after checking the G band. U is one of the lowest signal to noise bands, and so you would check it last.
Oh, there's a question in the chat. Oh, it's will diffuse light be in DP 0.2? But I think the answer is the diffuse objects weren't in the simulated images, and DP0.2 uses the same simulations. So there's still no like low surface brightness galaxies or stuff like that in DP0.2 because it wasn't in the DC2 simulated data set in the first place. Yeah. Pausing for any more questions.
I think there's one more question from Yanni. Is there a way for delegates to use the software to generate simulated images for particular pointings?
Oh, we already answered that one.
You did, okay.
Yeah,
That's
in the chat.
great, thanks.
Okay, we seem ready to continue.
Okay, give me a second to switch over.
While Yusra's switching over, I can add to the response about diffuse objects or low surface brightness objects. We're not in the simulated data set, but an excellent delegate activity might be to explore injecting objects into the data and then rerunning the detection and measurement algorithms.
Okay, if this is too small, let me know.
I think it's pretty good.
Okay, so we are going to load up notebook number 5. And I liked Alex's method of copying and pasting into a fresh notebook as well. I'm going to grab a new notebook and look at these side by side. Make this small. Okay, and please feel free to ask questions as we go. I'm not monitoring the chat, so if somebody could shout out the questions out loud, that would be helpful. And if any of the other data management folks want to answer, thank you, as feel free. I'm sure there's other people on the line who know more about various topics than I do. Okay, so first of all, I do not want to take credit for this notebook. I did not write it as part of the delegate curriculum. So thank you, authors, for the hard work in developing the curriculum. So the learning objectives for this notebook is to show you how to rerun some of these steps yourself. And this is important for reproducibility. And like one of the first steps in changing the processing is to, the first step in doing something different than what was done before is showing that you can reproduce something that was done before. Now, as a heads up, we're using weekly 33 at this point, and the DP0.1 data set was processed, I think, 2 years ago at this point. And so you won't necessarily get the same answers using this stack as you would have gotten 2 years ago. Config parameters have changed, and a lot has changed, but not as much as you would think. Okay, so first let's confirm what version I'm using. Weekly 33. I'm going to do some imports. Now I'm also going to, there's different ways to achieve some of the goals in this notebook. So I'll give some alternatives when I see them. So first thing to know is that these are very standard import aliases for stack packages. AFW is our core applications framework, and this is very common to see AFW image as the alias. So what happened for this one, you'll notice we're importing Lsst geom as AFW geom. This is because the very low level geometry methods in AFW geom were moved to a lower package, I forget how long ago, called just geom. And AFW now depends on geom, and this was done so that so other packages and other projects could use it. So I think when this notebook has used some examples from long time ago, which had the bounding box methods and objects and classes in AFW geom instead of geom. So what I'm going to do, so we're going to leave this here because I think you need it to run, but I'm also going to import this as geom, which is what we normally do. There's also an AFW geom, which includes the span set classes that you're going to see later as well. Okay, we're going to fetch the calyx or a calyx from the butler. Now, we're going to grab visit 512055. Now, for every visit, you can only put one filter in front of the camera at a time. And so the butler knows that this visit corresponds to filter I. So you actually don't need this, and it'll still work. Likewise, the detector can only be in one raft, and the butler knows that detector 75 is in raft 20. So it'll be smart enough to figure that out as well. So you can leave that off also. And we're going to grab this from the Db0.1 collection. And here we go. On outputs, the standard out will show up as pink. If it's just a warning, you don't have to worry about it. If it has the word error in it, then you do have to worry about it. So this, for example, is just a warning, and it's a warning because this data set was run with different middleware 2 years ago than we use now, and some of the expectations have changed. Okay, so this calexp has quite a few methods on it. I think of, so this is an exposure. Calexp is an exposure. It has a masked image, which includes its 3 planes. There are shortcuts to grab, image is an attribute of masked image. However, there are shortcuts that let you get image directly from the exposure. There's a variance plane as well. It also has models, PSF models attached to them. It has WCS attached to it. And it also has a photocalib attached to it. What is not attached to it is the background model. And Let's add that background model in right now. Actually, hang on. We're going to visualize this first before we add the background back in. So first, we're going to remove the detected mask plane, and that's because we're going to rerun detection later, which is going to reapply this mask plane. And let's take a look at what this calyx looks like. Okay, so you see you've got a 4K by 4K single detector image that has been background subtracted. The average background falls around to 0. So to add the background back in, we're going to fetch the background from the butler. Hang on. Yeah, I also have trouble talking and typing at the same time, so feel free to ask questions as I go. So the masked image allows you to you can do arithmetic operations on it. You can add to a masked image, you can multiply a masked image by a factor, and it's smart enough to, if you multiply a masked image by 2, for example, it's smart enough to double the image plane and then quadruple the variance plane. So what I'm going to do to this is add, let's first look at the background model. I'm going to copy and paste this from a different notebook. Hang on. Okay, this is what the background model looks like. What I'm going to do next is add this back. And so this masked image is a view into the masked image. I've just modified the masked image, which also modifies the exposure. So now when I visualize the whole calyx again, you'll see that this color bar is now in the around 4,000 instead of 0, because we've added the background back in. Okay, next step is to grab a cutout of this calyx. So this box 2i class is a member of Geom at this point. We're going to grab And box 2i, the I stands for integer. It just means that the endpoints are integers rather than floats. Box 2i has a cool method called include, which modifies the box to include whatever points or other bounding box you give it. So every time you call include, it will expand if the point is outside of the bounding box, or it will not change if the new point is within the bounding box. So this is one way to ensure to create a bounding box with a particular x min, y min, and particular height and width. Another way to do it is there's the constructor. Also, you can just give it the endpoints. You can also give it the min max, the XY0, and then an extent. I guess that's the one that we'll show now. So I'm going to give it the min, and then an extent with width. Spelled extent wrong. And this bounding box should be the same as the other one. Okay, let's look at what this cutout looks like. Okay, now you have a 400 by 400 pixel cutout of your calyx. And again, because I added the background back in, you've got an average of 3,000. Okay, so now getting into tasks. And after the top of the hour, in one of the breakout rooms, I can stick around and answer questions about tasks, and we can go through the rest of the notebook and answer more questions about pipelines. So tasks are the building blocks of the pipelines. They are hierarchical. That is, tasks can run other tasks as subtasks. And this is why there's such a large set of tasks, is because there's some tasks that all they do is run other ones. They are configurable. They have configs that you will set before instantiating them. So these are a selection of tasks that we are going to run. Tasks all have a run method. Actually, I forgot what I was doing. Copying and pasting. Okay. What's going on with the schemas, you might ask? The way that our measurement algorithms work is that you have to, the first thing you do is create an empty catalog, and then you run the run method of your measurement task, and it fills that catalog. But it has to know what columns it's going to fill before it fills them. This is why we make a schema first. And then when we instantiate all of these tasks that come next, we're going to pass this schema to it, and it's going to add columns that it plans on measuring later. So we're starting off with a very basic schema, the most minimal schema that you could make. And this just has an ID, a RA, a deck, and a parent, which is for deblending. So if a source is deblended, then it creates, like say a source has two peaks. It will deblend those into two sources. Each of those, the first row will stay as a row and will be designated as the parent. And then the two children will have its parent field set to the ID of the parent. So now you have three rows. One of them is the parent. Two of them are the children with the parent field set. Whenever you're working with catalogs from pipelines, the first thing you do is select on sources that have detect is primary equals true. What this is going to do is remove, if the deblender has been run, it's going to remove the parents from your list of rows so you don't get duplicates. Okay, so we need this schema. And like I said, the tasks are configurable. The pattern for configuring them is you construct them, you instantiate it, and then you can start changing things. So the characterize image task, this is the one responsible for measuring the PSF and background in the first iteration. So by default, let's see what it runs by default. By default, the PSF iterations are 2, but I want to change that to 1. So that's as easy as changing it to 1. Note, all your config changes must be done before you instantiate the task. So I'm now going to pass this config parameter to characterize image task. I think this none is unnecessary. Doesn't matter, doesn't hurt to have it in there. And now this creates an instance of characterize image task that has PSF iterations. It's only going to perform 1 PSF iteration. If you change your mind and want to change that to 3, do not change it in an already constructed task. You should never use configs to store a task state. This is because we want our tasks to be reproducible. And in order for that to be true, you want the config information that was run on a task to accurately reflect what has actually happened to the data. And so if you say I change my mind and I want to set this to 3, what you should do is change your config object and then construct a new characterize image task. With that new config, but we're going to use 1. Okay, we're going to do the same thing for source detection task. We're going to set a threshold value to 10. This means it's going to select all the sources that are above 10 sigma, and it's going to use threshold type of plain standard deviation. I can answer questions about that in the next, in the question and answer period later. And now we're going to instantiate source detection task using that config parameter. And we're also going to pass the schema in. And what this is going to do is it's going to add columns to the schema that it plans to measure. So this modifies the schema object. And then this same modified schema object, we're also going to pass to the blend task, and it's going to further add columns that it plans to measure. So now your schema has a lot more in it than first started. But when we actually run the methods on it, the run method on it, it'll fill those. It'll fill those columns. Okay, so we've instantiated all the tasks at this point, but we haven't actually got to the point where we were going to run them. And it's 1:02. Melissa, what do you think I should do? Should I go for like another 5 minutes, or should we save it for the breakout room?
Kind of trying to tell if this is a natural breaking point, then we should pause. If a more natural point is in 5 minutes, do 5 more minutes. Oh, looks like we're about to start 2.2 image characterization. So maybe this is a good point to pause.
Okay, we'll pause here. So we've instantiated some tasks, and the next step is to run each of them and then look at the outputs. So I will stop here.
Let's thank you, Yusra, for the formal presentation and then for the first bit of run through 5. Yeah, news reactions. And now we'll take a bit of a break. We'll do some more delegate profiles. We'll give you a chance to think about, I'm going to take screen sharing away for a sec. Let's fix this. Yeah, so this gives you a chance to think about breakout rooms. If you'd like to suggest another breakout room topic, stuff you want to work on today, you can pop it in the chat while we go through the next few delegate profiles. And then I'll add them to the list and I'll get a breakout room made for you. But we will come back to that and head down to, you should be able to see my screen. I don't have the, okay.
Yeah, good.
Okay, that's good. It doesn't have the box, but that's okay. So let's do a few more delegate profiles, and feel free to like get up and stretch and stuff while we do this part at the midpoint. First up, Matt. Do we have you with us?
Yes, I'm here. Hi. So I'm Matt Wiesner, and my student is Marcelo Avila. So I'm an assistant professor of physics at Benedictine University in Lisle, which is just outside Chicago. We're most active in the dark energy science collaboration. So I'm interested in learning to use Dp0 and learning to use the butler and accessing images. So a project I'm working on in the desk is trying to resimulate a tiny section of DC2 while including kilonovae. So the result of a colliding neutron stars or a neutron star colliding with a black hole, you can get this burst of light. So we're trying to simulate these fairly rare transients by rerunning DC2 using FOSIM. And so one of the things I've done with Dp0 is I've made some modifications to Notebook 2 to find objects over 1 square degree using 4 separate quadrants. So and that was with help from Douglas Tucker and Sahara Lam, who are working with me on this project. And I'm definitely interested in collaborations. Thank you.
Awesome, thanks, Matt. That sounds like it would make a great delegate presentation for later on in our assemblies if you're interested. People would be interested to see what you did. Yeah, thanks for that. Chao Chu, are you here?
Yeah, I'm here. Yeah, hi, I'm Chao Chong, just call me Chong. Yeah, I am an associate professor at National Central University. It's located in Taiwan. That's mean now it's 1 a.m. Yeah, here. So in general, for my interest is the variable star. Is a classical pulsating star and distance scale. For the Dp0, I want to explore the variable star, like because there's a 10% star variable star, and especially for the RRAs. And very thank you that that's one the notebook 209 is looking for the RRA. So I'm very happy to see that, and also trying to get some light curve for some random selected small regions, but it's not very efficient as you know. So hopefully can learn more about how to get a light curve in the futures. So whoever working on the wearable star, I'm happy to work together on this part. Yeah, that's all.
Thank you. Thanks very much for that. Yeah, I know a lot of people are interested in time domain, and everyone's going to be really happy when DP0.2 comes. We all have, yeah, different image stuff. But in the meantime, yes, work to do time domain stuff. I think a lot of people want to collaborate with you, so that's cool. Sarah.
Yeah, thank you. I am Sara Bonito. I'm a staff researcher at the Italian National Institute for Astrophysics at the Observatory of Palermo. I'm a member of Transient Variable Stars, Stars Milky Way Local Volume Science collaborations. My main interest within Rubin is on young stellar objects and their variability, star-forming regions, but also how to use Rubin Science platform, work on survey strategy optimization, and I also work on inclusion in science. For the DP0 specific interests, I'm chairing a task force for DP0 delegates in the Science Collaboration on Transient Variable Stars, DVS. So the idea is to continue the work done during a previous task force on Rubin Science platform evaluation and through the Stack Lab involvement. And the ideal main aim of this task force is the transfer of knowledge of science collaboration members for tutorials, student mentorship, tests on the Portal and Jupyter Notebooks aspect of the Rubin Science platform, software developments, light curves. And here I show you a plot from our recent cadence node for the optimization and survey strategy for young stars variability. And definitely I'm interested in collaborating with other DP0 delegates interested on the variability, stellar variability in general. Thank you.
Awesome. Thanks, Sarah. Yes, another person interested in time domain, as many are. Nacho.
Hi, can you hear me well?
Yes, we can.
Okay, so yeah, thanks. So I'm Nacho, staff researcher at AlSayyad in Madrid. Currently member of the Dark Energy Science Collaboration, as many of my other colleagues here. My main interest is in cosmology with Rubin data, actually spanning on all scientific topics related to fundamental physics that we can do with this data set, with an emphasis on large-scale structure and specifically understanding the robustness of the cosmological lambda CDM model. Also have other side interests as doing object classification, which is going to be a lot of fun with Rubin, especially applying machine learning approaches, but basically playing around with different algorithms. Also, outreach to high school students is also another of my passions, and ideally combining all these three aspects, that would be like a great project for me. As part of the science release and validation team of DESC, we're working on having or creating like a small characterization test suite that can run efficiently on these sort of data previews and eventually larger data sets, data releases. So this kind of work is, developing this kind of tests and running them at scale will be really interesting for me. And if anyone is doing or developing this kind of things in other science collaborations, I'll be very happy to get in touch with them.
Cool, thanks, Nacho. Object classification might make a good DB0 working group. I think a lot of people would be interested in that kind of thing and interested in sharing notebooks on that. Thanks. I think last delegate profile today is Louise. Yay.
Hi, my name is Louise Edwards. I am an assistant professor at California Polytechnic State University in a small town called, beautiful on the picture here, a town called San Luis Obispo in California. My interests are galaxies. I'm part of the galaxy group, and in particular, galaxies in different environments. So as part of that, I'm also interested in diffuse light and clusters and superclusters and filaments that connect them. whether or not galaxies look different in those different environments. So I've been playing around, putting together stuff from all the different notebooks that are available, which are so helpful in trying to use the truth tables and find filaments, large-scale filaments, and compare them to filaments I find using like RCS methods and different types of options out there for running KDE models, like in SciPy versus other packages out there. And I am happy to collaborate.
Great. Thanks, Louise, and thanks also in advance because you've volunteered to be one of our first delegate presenters in November. We're very excited about that. And also large-scale structure is one of the Dp0 working groups that's sort of already off the ground a little bit. You guys found each other and yeah, I've been working a bit. So that is awesome. So thanks all our delegate profile presenters today. Thanks very much for being here, sharing your work. Hopefully that was fun and useful for everyone. We'll do this again in 2 weeks with more delegate presenters. And for now, let's try to set up some breakout rooms. So far we've got the usual thing that we do where the main room will stay open for questions, people having access issues, people who are having issues with like notebook number 1, if you have sort of like any basic access issues or Python questions, some of us will stay here in the main room for that. I'm gonna open up, I'm gonna start making breakout rooms. And we'll have room number 1 be, just gonna name it Yusra and Pipelines. That will be room number 1. So if you have questions for Yusra, you can go into room number 1, maybe like do a quick round of Q&A about Yusra's presentation or anything that about notebook number 5 that has been so far presented. And then everyone in breakout room number 1 can just sort of keep going with notebook number 5, and you can see how far you get in the rest of today's session. I'd like to try and start a working group for supernovae, although I suspect that breakout room number 1 is going to be super popular. So I will say also that if you are interested in supernovae, but you also really want to go to breakout room number 1, go to breakout room number 1. We'll try and come back to supernovae and stuff again next week. So we're looking at supernovae for Dp0.1. It's something we can do next week as well, since we have to pick between the 2. But I'll go hang out in breakout room number 2 for a moment and see if anyone wants to talk about supernovae. I'm gonna check the chat really quickly. Is anyone who's been working on other stuff? Any of our other proto working groups like large scale structure, or if anyone wants to co-work on the grants. Yeah, co-working on the grants. It's a really good opportunity for TVS, Stars Milky Way Local Volume or Solar System. So I'm gonna make a 3rd room for that. Stars Milky Way Local Volume. So I'll make that breakout room number 3. And a room for resolved stellar populations, absolutely. Alex, I'm gonna make you facilitator for room number 4. And for the grants, Louise, just since you suggested, I'll make you a sort of official facilitator for that room.
Okay, except I think I'm gonna go to resolve stellar populations.
Okay. Is there anyone else interested in grants? I'll open the room up anyway, even if someone doesn't want to take over facilitatorship of that room. Just let people chat in there.
Melissa, quick question. Is it possible to record a breakout room? I have a concern that there might be a lot of people who would like to participate in more than one. And I was thinking that maybe we should try to record the one that Yusra is going to be facilitating.
There is not, but what we could do is, the thing is, I never like to send someone into a breakout room to just sit there by themselves. So that's why we don't have the general RSB Q&A as a breakout room, because yeah. But what we could do here is, okay, let's do this instead. Let's, so that we can keep recording.
Yeah, because it was really a very interesting set of presentations, but I think that it's obvious that they will continue.
Okay, so here's what we're gonna do.
That's a good plan, I think.
So we'll make room number 1 an open room for a general RSP Q&A. But if you have general questions, post in the Zoom and someone will join you in that room so that we don't have to have someone just sitting there for an hour with no one to talk to. But if you do have a question, we're always happy to pop into that room and just help you with your access issues or whatever like that. So just ask in Zoom, say, can someone help me out in room number 1? Totally fine, we'll do that. We will leave Yusra in this room so that we can keep recording, so in the main, and then all the other breakout rooms stay as they are. So all the rooms are now open. So I'll give you a moment to go to them. And also regarding the grants, I did in the Zoom chat, just put the link. So anyone who wants to talk about grants, you can use the website for the grants proposals to guide your conversation. Okay. So I'm gonna go sit in the supernova room and see if anyone wants to talk about supernovae, and then we might rejoin this room after that. Just sort of giving it a second in case any questions come up. Other than that, Greg and Yusra are in charge of this main room.
Sounds good.
So, okay, I'm leaving now.
Thank you, Alyssa.
Nice.
So Melissa, I want to stop sharing so Yusra can share if necessary, if that's okay.
Okay, got my first question. Could you scroll back and recap how you added the background back to the image? Yes, I would love to. I will even, and if you're interested in backgrounds, we can even, we can spend some more time on that as well. Let me share my screen again.
Looks good.
Okay, great. Okay. So the first thing to do is to grab the background model from the butler. The background model is there's two background models actually. So you remember in the slides I said that there's a background model that's produced by characterize image task. That's this background model. There's also a full focal plane background estimation step that happens afterwards. This, you'll see, only offers like a very slight minor correction on this polynomial background. And this is because I think the backgrounds added to DC2 were just, I think each CCD just has one offset, like one flat background, either that or like a ramp. Simon, I see you.
I think there was a moon aspect, which is just basically a linear. If the moon is up, I think there is kind of a linear gradient.
Yeah, I know. So on that, do you remember in that full focal plane image that I showed in the slides, that was a post ISR CCD with the background still in, and there was a flat ramp. The thing that I'm not sure about is I'm not sure if so there's definitely a ramp applied to the visit, but the question is like per CCD, like across the pixels, is there one? So what I heard was that at least for a single CCD, it was constant, but I might be wrong about that. Okay, so this first initial background model is called Calyx background. The second one, which is not going to be available in DP0.2, it's called Skycore. So I'll show you this now just for fun, but you're probably never going to use it again. And these background models this is not, has a method called getImage. What this is going to do is create an image out of this background model. And this image is what you're going to apply to the masked image. Okay, so this masked image now has the background back in. Let's do the reverse and subtract it off. Wait, how did I do that? Okay, so this masked image variable points to a view of the masked image in the Calyx. I'm going to subtract off this background model, which should give us the original image. So when I visualize this, we should be back to 0. Yep, back to 0. And now I'm going to add it back in to get us back to the 3000. Now let's do the same with Skycore. First, this is the, no. Okay, and look at the kind of range we're looking at here. Skycore, the thing to know about Skycore is that, so it it's centered around 0, and it's a correction to the original background model. So you don't just replace Skycore here and get the Calyx with a different background model back in. You have to add the background and then subtract off the Skycore. And this might be overkill, but first let me getting it back to 0 again. Okay, and then we're gonna add it back in. Add the background, subtract the Skycore, and then we get the fancy backgrounds. Is this clear enough? Did this answer your question? Okay, any other questions? All right, excellent. What else? Is there any way to export the image we are looking at as a FITS image, or can it only be plotted outside the notebook? Yes, you can export it as a FITS image. One of the methods on exposures is, come on, tab. Okay. Sometimes my tab complete works, sometimes it doesn't. calexp.writeFits is the method that you are interested in. I don't, and I don't know where on file system these are recommended to be stored. Simon, do you have recommendations for where to put this?
I mean, if you want to share them, I think the /project space is the place to put them. There's also the /scratch that you can use. It's important to note that the writeFits method writes a FITS file that the AFW exposure knows how to read. So it's not just writing like a single image plane. It's actually writing a pretty complex FITS object that you could put it, read it into DS9 if you want to and that sort of thing. But it's also, you could also reconstitute it in Python if you want to.
Okay, I got into some weird state where I no longer have a
Yeah, you'll have to start from the beginning.
Okay, sweet.
Yes, sir. There's someone in the Q&A, the general Q&A room. I'm just going to head over there.
Okay. I'm going to run up until this point in the original notebook. Anyway, right. Hopefully that answered your questions about writeFits. Okay, any more questions before we move on to image characterization?
Yusra, can you see the Zoom chat as you go?
Yes, I can.
Oh.
Okay, we've instantiated characterize image task, and we're going to run it. Tasks usually have a run method, which contains the meat of what that task is supposed to do. The tasks return something called a pipe base struct. This is a fancy dictionary. I'm gonna add this. Okay, you can see output, it's running. Now, warning, warning, warning about what we're doing here. PSFs, so the calexp, the characterized image modifies the calexp. Calexp, so it will actually subtract a background off of calexp and store it elsewhere. It also attaches a PSF model to the exposure. This PSF model, show you what it is of type PSFX PSF. It's spatially varying, which means that it has a different shape depending where in the detector you're looking. So we have this method on PSF called compute shape, and it will give you an answer if you don't provide a position. However, this has caused much confusion in the past. People forget to add a position to compute shape and get back nonsense answers, and then spend a lot of time trying to figure out why they've got nonsense answers. Since weekly 33, which is what we're using for this notebook, we've actually deprecated calling compute shape without a center. And so in a future version of the pipelines, you are going to have to supply a center to a position to get a shape. So let's just make one. So one easy choice is to just get the center of the bounding box of the CalExp. And I'm not going to run result. I'm not going to run characterize image again because it's the part that takes the longest. Okay, so this gives you roughly the same thing. Let's pick something else. I could do the end, which should be a corner. This is gonna complain because the ends are a different point type than point to I. Wait, no, the ends are point to I's, but we really want a point to D. That's a floating point. It wants a floating point, not a integer point. So that's easy. You can just turn one into the other. So I'll show the difference. Okay. The PSFs are very similar. And then you can also get a WCS now, which has the measured pixel scale. So now that we've had basic PSF model, basic WCS background estimation done, we can now run source detection task. Source detection task is a task, so it returns a struct. If you want to see what's, okay. See, the original notebook does this already. If you want to see what's in your struct, there's a number of different pieces of data in here. There's the positive footprint set, a negative footprint set. If we had changed the config parameters for threshold polarity equals both, there would be a negative footprint set in here. However, we had the default threshold polarity is positive only. It's by default, it only selects positive sources. So this is none. I don't know what the factor is. I will get back to you on that. There's a background model returned, a number of positive footprints, a number of positive footprint peaks, same with negative, although they should be 0 and 0, just to double check. neg should be 0. This should be 0. The rest of this should be 0. Those are the number of footprints, number of peaks, because a footprint can have multiple peaks. And then we have footprint sets and a source catalog. Sources. Now, this we've only run detection. We haven't run measurement. So you're not going to find, sorry, you're not going to find measurements in here, but you are going to find rows with rows and everything except for pretty much everything is going to be nan. But this is going to be filled in once we run measurement. Questions so far? Okay, don't see any. Okay, here, so in the notebook that you have a copy of, it shows you how to write both the source catalogs and the exposures. Okay, now we're going to run source to blend task and source measurement task. Okay, so start making a copy of the source catalog. We recommend that you do this because it is currently before you make a copy, it is not contiguous in memory and cannot take advantage of I'm not the best person to ask about AFW table. So if somebody can give a concise explanation for why you need it to be contiguous to memory and what benefits you have, feel free to tell me. Okay. So you'll notice we've got now more rows than we have before. This is because we ran the deblender, and the deblender now has 1 row per peak rather than 1 row per footprint. And we have the measurements filled in. If you, okay, so there's, you can use whatever data type you prefer. Sources is a AFW table object. Its only benefit really is that it's a C++ object. So if you're writing C++ code, this is what you want to use. But if you're doing Python analysis, most people are used to working with AstroPy tables or pandas tables. And to get a pandas table, what we usually do is two pandas. And now you've got the same thing as a pandas table. Okay, I believe this is a review of last time. This is the 4K by 400 by 400 bounding box from before. We are displaying sources as red crosses and orange circles. If you're playing around, you can start earlier and change your threshold to something other than 10 and watch the number of sources increase or decrease depending on your threshold. there's different threshold types. Standard deviation just says it interprets the threshold value as sigmas. So if this were 5, you're detecting everything above 5 sigma. There are two types of sigma style threshold types. There's standard deviation and pixel standard deviation. The pixel standard deviation is per pixel, but this is not the recommended threshold type for detection. The standard deviation uses one threshold for the whole image. Okay, now fun with, okay, any questions about source measurement task before we go on to what these funny footprint things are?
I missed a little bit the part you were saying about threshold type being standard dev. Were you saying there's options?
Yes, there are.
I missed it. What are the options?
Okay, threshold type. Nope. I'm going to rerun this. Okay, so the reason it's complaining is because remember that each of these, instantiating each of these tasks adds to the schema. And so what I'm trying to do is take the same schema that I had before and add columns that already exist to it, which is why it's complaining at me. Hang on. We're going to, so the way to do this is help source detection task, config class. Okay, threshold type. The allowed values are variance, standard dev, value, pixel standard deviation. Value is useful if you've already created a Chi image, like you say you've taken an image and you know that it's a likelihood image already and you just want a threshold on a flat value. Like I think this is used for finding defects in flat fields and stuff like that.
Okay, so that's how I would find other things to use.
Mm-hmm.
Yeah, cool.
Okay, so source detection task produces these funny things called footprints. Footprints they're the geometry of pixels that are above the threshold. They have a, you can get them in the form of a span sets. Span sets are a very low level, very fast geometric class that has a lot of very useful methods on it. You can dilate them, you can erode them. Whenever you find yourself wanting to manipulate a funny shape that you want to, that doesn't have, it isn't a polygon, but rather like a shape of pixels, span sets are what you want to use. you can make funny shaped regions and then manipulate them using these methods. And you can test whether they overlap, whether they're contiguous, whether they intersect. Make unions of them, you can split them. The expanses are fast and very cool. Okay, so what span sets are, it's a map of which pixels are part of your region, which pixels are outside your region. And like Melissa and Alex pointed out, you can almost see the shape of your footprint by just looking at the ones and zeros in your span sets. These are footprints. Heavy footprints contain the actual pixel values that correspond to the ones in the span. The footprint set that we have, the span set that we have is, the footprint is, okay, so this is the, FPS is the list of footprints. We're grabbing the first footprint, period. It is not heavy. In order to make it heavy, that is to grab the actual pixel values, you have to call make heavy and grab the masked image. Okay, and then now that the footprint set is heavy, we're gonna call this heavy footprint set, HFPS. And this is the, just to show you that it actually has the floating point pixel values in it now. Okay, this is what the image looks like. The pixels that are outside of the footprint here are being set to 0. This isn't a cutout. This is a visualization of the heavy footprint, which only has pixel values where the detection was above threshold. It also comes with a mask. And visualizing this mask plane. So each bit in the mask means something special. You can get the meaning of each bit by requesting the get mask plane dict. So if the first bit is flipped, that means that a defect overlaps that pixel. And you can probably guess what each of these means. And this is just a compact way of storing a mask. So in this region, the detected bit is flipped. And then for just this region that's yellow, the detected bit has been flipped and so has edge. And you can, let me show you how to. Let me show you where I was playing around earlier. Okay, any questions while I dig up something?
I had a question, like when we did the FPS.get spans and you see the 0 and 1s and you just print out the array and it looks like it has the same shape as the footprint when you plot the footprint, like as a little image, but then the get mask array with all the numbers 48 and 32 doesn't have like the same shape as when you just look at the mask array. Should it? Why is it different? Do you see what I mean?
It should have the same shape. Let's. Sorry, which one doesn't have the same shape?
It's the heavy footprint, the get mask array, when it prints out those values. Yeah, further down. Yeah, there. It's not like the same shape, like when you just print out the zeros and ones, like you can see when you compare the image.
Okay, that is. That is because. Let's think of how to demonstrate this. These correspond to the pixels in the span. The span set shows you where those pixels fall in an image grid, which is why to go from this to this, you need to use the span set geometry to lay this mask array out correctly. There are other ways to do this too.
I see. So when we print out the mask array, it's only printing out the values of basically pixels that were a number 1 in the first one. So that's why the shapes don't match.
That's right.
Oh, yeah.
So one thing you can do.
Oh, and the ones with the 48s and 32s, I didn't actually notice it's flattened. It's not like, yeah, it's not.
It's not 2D, or sorry, it's not.
Yeah.
Okay, thank you for the question. Any other questions? Okay, while I'm here, if you have any questions about tasks, a very good place to go is pipe base, which is where tasks are defined. Pipe base includes an overview of the task framework. A lot of this is still true. As a warning, command line task is the Gen 2 middleware entry point to tasks that you do not need to know about and will be going away at New Year's. So everything else other than command line task and task runner and the argument parser is still valid.
Is the argument parser valid? I thought that was Gen 2 as well.
Maybe I mumbled it. That was on my list of things that are no longer valid.
Okay. Task runner is also dead.
That's right. So the things that are dead: command line task, argument parser, task runner. Tasks still produce structs, and you can still time them. Thanks, Tim. Okay, we've got 4 minutes left.
So this has been excellent. It's been like super useful for us as well. You added a lot of value to this notebook with just like different options and different things you've been showing. We've been keeping a side list of updates to add to this notebook to just, yeah, make it a little more enriching based on a lot of the things that you've mentioned. So yeah, we're planning to do some updates to this notebook based on the things you just presented. So it's been good.
The notebook fit perfectly with the topic for today. So thank you.
And I wanted to thank you also when you were giving the presentation, like you gave our delegates a lot of context for what you were saying by linking it to things that they had learned in the past, and then also linking it forward to DP0.2. So I just wanted to make a note that I really appreciated that. And I think the delegates will as well, to just have that context for everything that you were saying.
Thank you so much for having me.
So let's give Yusra like another final round of applause. Use your reactions, use your video. And as usual, the community engagement team, we're going to sort of hang out here as people leave. And so if you have any final questions that you just didn't want to bring up before, now as people start to leave, you can hang out a bit and we'll stay here and get them answered for you.
And of course, we'll be on the Stack Club meeting next Friday in the case if you wanted to sort of elaborate on something when you thought about all this stuff after we went home, we'll be here. And then in 2 weeks, we're going to have Keith Bechtel, and he will be presenting his stuff on visualization primarily. And I think, if I understand correctly, Leanne will be the host.
That's the plan. Yeah, thanks, Greg.
Thank you, Yusra.
You can see people are still in the breakout room, so I don't want to like actually end the session yet if they're in the middle of a conversation.
Yeah, I think Alex is pretty busy working on some of these stellar stuff. Resolve stellar populations.
Yeah, that's cool. Oh, I should mention too, Yusra, while we have you, as you've been looking at notebook number 5, if you like have a list of updates, or if you made updates like while you were working through it, we would love to ingest those as well.
Okay. I should just make a pull request.
Yeah, you could make a pull request. There's actually, I'll post, where did it go? Alex opened an issue. Alex opened an issue where we can talk about making updates. So either you could just like make them yourself and then make a pull request, or just give us a list of the stuff to be added, like whatever works for you. I put it in the Zoom chat.
Thanks.
Yeah.
It looks like people are coming back from the stellar populations breakout room.
Oh, yes, I see that. Yeah. Okay, looks like I can safely close the rooms now. Okay, they'll close in 50 seconds. Yeah, so everyone who's here too, if you have things that we should add or change about notebook number 5 based on today's presentation, do add them to this issue that Alex opened and then I put in the Zoom chat, and that you should be able to see how to go and resolve stellar populations. Anyone want to comment on what's going on in there?
I think Sid's going to finish it off. The paper will be ready, you know, next week. No, I'm joking. I'm joking.
Like, what?
Very clear.
Oh, you tricked me. I was like, oh my God, the first Db0 paper.
Sid, do you want to, is Sid still here?
I don't think so. Oh, yep, there he is. Yeah.
Yeah, sorry, I was just messing with file permissions. Yeah, so basically Alex was driving most of the time, but we were looking at the, I guess one of the possible stellar selections for the Dp0 catalog and comparing that to the truth and seeing kind of how well that does. And very, I guess, pleased by how nice the completeness curves look. Alex, I'm not sure if we have any other like big takeaways for the moment, but.
Yeah, I thought it was cool. It was sort of like the first data quality characterization stuff you would do. So we're trying to characterize the stellar completeness well, we're trying to define the stellar sample, define the stellar completeness, and then characterize the photometric uncertainties as a function of magnitude. And then I think with those things in hand, we can plug it into other machinery that we already have from other surveys to generate simulated stellar populations and inject them into the catalogs.
Awesome. Okay, that sounds super cool. That sounds like it might turn into a delegate-led presentation in a month or two, maybe.
Yeah, don't scare Sid away.
Yeah, totally voluntary, but it does sound like it's moving in a useful direction.
Yeah, definitely.
Yeah, cool. Yeah, don't worry, that was not a commitment. It's just more of an invitation. you're not locked in. Yeah. Okay, wonderful. Very successful day. I think that we are all done now. We can go off the rest of our days. Have a good day and a good weekend.
Yeah, once again, thank you very much, Yusra.
Yeah, thanks, Yusra.
Thank you.
Thank you.